Welcome to another lecture video. In this video, we're going to take a look at something called L'Hopital's rule. It's in section 4.4 of the text. We just finished up the derivative tests on Monday. The derivative test plus L'Hopital's rule that we'll talk about today is what you have coming up for your quiz this Friday. Some of the announcements just real quick this week, kind of see where we are in the course. First and second derivative test video from Monday is up. Make sure you go through and read section 4.3 and 4.5 for that. Today we'll talk about L'Hopital's rule, and together those two will be the quiz this Friday. You do have 2 homework sets due this weekend. You can go ahead and get started on homework for section 4.3. We've wrapped that up on Monday. And then after we finish today's topic, L'Hopital's rule, you should be all set for 4.4. Which is also due Sunday. I will remind you that there are a ton of resources for these topics online. For example, the derivative test section that we just went through, there are online notes for all that stuff that we did on Monday. Here's the video from Monday, and then we have a couple of additional videos. The same thing's going to be true of today's lecture with L'Hopital's rule, so make sure that you're taking advantage of the resources that are being put on Canvas for you. All right, so I want to start with a very simple question, but it'll turn out to be a very important question in the grand scheme of what we're going to talk about today. And that is, which of the following limits are indeterminate? Now, we've talked about indeterminate forms a little bit this semester, but we're going to formalize that today and discuss exactly what it means to be indeterminate. Remember, an indeterminate form is any form upon plugging in the limit where you're unsure of what the answer is. For example, on this very first one, if you plug in x equal to infinity, you will get infinity over infinity as the form, and this one is indeed indeterminate. We've talked about that one multiple times this year. If you have infinity divided by infinity, the infinity in the top wants to make the fraction larger. The infinity in the bottom wants to make the fraction smaller. It's a sort of a tug-of-war here, and so who wins? We don't know. Sometimes the bottom wins, sometimes the top wins. In this case, because the bottom is an exponential, it's growing faster than x squared, so the bottom wins, and this particular limit will be 0. But that's not always the case. So what I want you to do is pause the video for a second here, go through the remainder B through G and see if you can determine if the forms that appear are determinate, like you can determine an answer, or indeterminate. All right, if you haven't paused the video yet, you should do so. We're going to take a look at each of these together. So we're going to start here with B. If I plug in the limit as x goes to 0, that's sine of 0, which is 0, and then x equal to 0 in the denominator, you get 0 over 0. 0 over 0 is basically just the reciprocal of this one, which means it's just as indeterminate because a 0 in the numerator of a fraction makes the fraction smaller. And remember, this isn't 0. This is really small numbers, so small numbers that are heading towards 0. That makes the fraction smaller, but if you do that in the denominator, small numbers in the denominator make the fraction larger. So there is that sort of indeterminate struggle between the two. So this is an indeterminate form. On C, if you look at C, this is 0 to the 0, plugging in x equal to 0 there. And this is also going to be an indeterminate form. If you think about it, if you have numbers that are really, really small for the base, the overall size of the exponential there becomes closer to 0. So like if you have 1 100th squared versus 1 1000th squared, the 1 1000th term will be much smaller. So as a whole, smaller numbers in the base make the exponent smaller overall. But if you have numbers approaching 0 in the exponent, then if they're approaching 0 in the exponent, then overall the power is approaching 1, right? Because we know anything raised to the 0 is 1. So you have this indeterminacy between the base wanting to make things closer to 0 and the exponent wanting to either oscillate things because it's a negative exponent or make things closer to 1. So there are many different possible outcomes for this one. So this is also indeterminate. If you look at D and plug in x equal to infinity, you have e to the negative infinity. Well, this e to the negative x is a decaying exponential, right? So this is what the graph of e to the negative x looks like. And as x goes to infinity, you can see that the graph goes to 0. It has an asymptote there. And then the bottom would be infinity. So this is a 0 over infinity type. Is this an indeterminate form? Well, infinity in the bottom would want to make the fraction smaller. 0 in the bottom would also want to make the fraction, or 0 in the numerator would also want to make the fraction smaller. Both parts of this are trying to make the fraction smaller, so there's nothing indeterminate about this. This is going to converge to 0. So that is not an indeterminate form. All right, if you look at E, if we try to let things go to infinity here with E, you have a 1 plus 1 over infinity to the infinity. Well, if you look at 1 over infinity, 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000, those are getting smaller as the denominator grows. So that's heading towards 0. So this ends up being 1 to the infinity in terms of the form that it has. Now this one's tricky. I'm betting most of you said the answer here was 1. Because you are correct, if you do multiply 1 by itself an infinite number of times, you do get the answer 1. However, for this particular problem, you don't actually have a static 1 here. This value is still here and constantly changing, but it's getting smaller. So imagine that you have a number that's just to the right of 1. Say you look at 1.01 to the x. Well, as x goes to infinity, so as x goes to infinity, this value, because it's bigger than 1, it keeps getting bigger. So 1.01 squared, 1.01 cubed, and so on, those numbers keep getting progressively bigger. This is going to diverge to infinity. But if you looked at a number just to the left of 1, as x goes to infinity, remember numbers between 0 and 1, like say 0.5. If you take 0.5 times 0.5, you get 0.25. It gets smaller. So numbers less than 1 in absolute value, when you exponentiate them, the overall value gets smaller. So this is actually going to head towards 0 as x goes to infinity. And that's what makes 1 to the infinity indeterminate. It depends on how the value in here is approaching 0 as to whether we're going to get bigger or smaller. This is a very unstable, hence indeterminate form that we have here. We just don't know which of these cases it might be. And it might actually be the case that we end up getting 1 out of this, but we don't know before working the problem further which of these cases is going to happen. So remember, 1 to the infinity is an indeterminate form. Let me just go ahead and box in the rest of these because I want you to memorize these forms. 0 to the 0 is an indeterminate form. 0 over 0 is an indeterminate form. And infinity over infinity is an indeterminate form. All that means is that if you plug in values into your limit, if you directly substitute into your limit, and you get one of these 4 things, you don't have an answer. You don't know the answer. So this one is indeterminate like the others. All right, if you look at f is 0 for the base, 1 over 0, and if you think about 1 over 0, that's becoming very large. So this is 0 to the infinity. So the question is, what do we think about this one? Well, if you think about 0 to the infinity, this is a number which is heading towards 0 for the base, and we're repeatedly differentiating it. That's just like this case right here. You have a small number that's heading towards 0, And as you exponentiate it, it gets smaller and smaller itself. So both of these are heading toward the same goal, and that is of making the whole thing go towards 0. So this thing converges to 0 over time. So it is not indeterminate. So D and F are out. Finally, let's talk about G. If you plug x equal to infinity in for the limit on G, you'll get the square root of infinity minus infinity, which is infinity minus infinity. This one is the most misused one, I think, on the list by students. Most students want to say that this is 0. Let me explain quickly why it's not. Consider two functions which you know well. We'll look at the function y equal x. And we'll look at the function y equal x squared. All right, so consider the limit x squared minus x. So x squared minus x is the vertical distance between these two. So initially that number is negative because x is actually bigger than the function x is actually bigger than the function x squared up until you hit 1. Then past 1, x squared just skyrockets past it, and the gap between them grows bigger over time. So as x goes to infinity, the gap between these two graphs becomes infinitely large. This limit is infinity, because the limit is basically telling me how big does the gap between these two, that would be the gap, how big does that gap get as x goes to infinity. However, if I simply reverse the two, then the gap here would be the distance from x up to, which would be in the negative direction, x up to x squared. It would be a negative distance here because we're going in the opposite direction. If you take that, that would be negative infinity. Now here's why this is indeterminate. This is an infinity minus infinity. This is an infinity minus infinity. And we have two different answers. That's as simple of a case as I can make. There are many different things that can result from this one. So infinity minus infinity is indeterminate. You can't know what the answer is. The answer is not necessarily 0. In fact, rarely is the answer 0. So this is also an indeterminate form. So these aren't the only indeterminate forms in mathematics, but they are the 5 indeterminate forms that I'm going to stress in today's lecture and that I expect you to be aware of. Now, we don't have many tools at our disposal, at least right now in the course, for handling indeterminacies. We can do some algebra like we did earlier in the course and hope things work out. But if there's not a way to algebraically manipulate or reduce some sort of fraction or something like that to get an answer, then we don't really have a tool for evaluating indeterminate limits. And the tool that we use is L'Hopital's rule, which is what we're going to be talking about today. So suppose that one of two cases holds. You have a fraction of the form f of x over g of x. So case 1 is you're looking at the limit as x approaches a of f of x over g of x. You plug in the limit. So the limit of the top is 0. The limit of the bottom is 0. You get 0 over 0 type. So that's a type 1 indeterminacy. Or you plug in the limit as x goes to a of f of x over g of x, and it turns out that both of them go to infinity instead, and this could be plus or minus infinity. Then that's an infinity over infinity, which is a type 2 indeterminacy. So L'Hopital's rule says if you have a limit problem where the function in question can be written as a ratio, and the limit of the ratio turns out to be one of these two cases, then what you can do is the following. If your functions f and g both have derivatives on the interval containing the point A, so in other words, you're not at a corner point or you're not at a vertical asymptote or something like that, you can take the derivative near A, then you can substitute the limit of the original ratio with the limit of the derivatives of each of these. Now, this isn't quotient rule. This is the derivative of the top and the derivative of the bottom. You can substitute this original limit for this limit, and as long as this limit exists and is finite, then the new limit is indeterminate. Okay, so this new limit must exist, be finite, or be plus or minus infinity, and then this will work out. So you can't take the limit of this thing, and if the limit is undefined, tell me that the original function is undefined. That would mean that L'Hopital's rule actually fails. The only time that this gives you an answer is if the limit, this new limit that you calculate here, exists and turns out to be finite or plus or minus infinity. If it gives you any other answer, undefined, indeterminate, whatever, then either if it's indeterminate, you can reapply L'Hopital's rule. We're going to do an example of that. But if it's just straight undefined, you can't say anything about the original limit. All right, I want to prove this, and I'm going to prove it in I think the 0 over 0 case is the one I'm going to look at here. Yeah, so I'm going to prove the 0 over 0 case that this works out. The infinity over infinity case is really similar. So here's a go at the proof. I want us to consider the limit as x approaches a of f of x over g of x. Turns out to be 0 over 0. And that f of x and g of x are differentiable in an open interval containing the point x equal a. So I'm just assuming the assumption of the theorem, okay? So this is our assumption, and I shouldn't say consider, I should say assume. So I'm going to assume that this is true. All right, then what we can say is the following, and here's the kind of the crux to the whole proof. If you take the limit as x goes to a of f of x over g of x, because this is 0 over 0, the 0 on the top means that, well, I should say, because the function is differentiable, remember that automatically implies that the function is continuous. And if we know the function is continuous, then that implies that the limit as x goes to a of f of x equals f of a. So we know that f of a is a defined value here, and that according to our assumption, the limit as x goes to a of f of a is 0. So f of a's value is 0. That's going to be important. But first, what I want to do is this. I'm going to take f of x, and I'm going to divide it by x minus a. And I'm also going to divide g of x by the same thing. So basically, I just divided the top and bottom of this expression by x minus a. Okay, next, I'm going to use the line of reasoning that we just outlined here to say, well, okay, I can take, because I know that f of a is 0 and g of a is 0, then I can take f of x minus f of a over x minus a, and g of x minus g of a over x minus a, and this will be the same thing as what I have right here. Now, algebraically, this to this makes sense because I'm dividing the top and bottom by the same amount. But here, this doesn't make any sense unless I know something special about f of a and g of a, which I do, I know that both of these are 0, so all I did really was subtract 0 from the numerators of each of the fractions on the top and the bottom here. In doing so, though, I create forms that I'm familiar with. Remember, our limit laws say that if you're taking the limit of a ratio, it's the ratio of the limits. So I can write this as the limit as x goes to a of the top divided by the limit as x goes to a of the bottom. And I should recognize these limits from the course. This is the definition or the form of the derivative function at a. So, you know, the way to write this is f prime of a over g prime of a, which is the same thing as saying the limit as x goes to a of f prime of x over g prime of x. So what we have here is a situation where I can exchange the original limit with the limit of the ratios of the derivative instead and maintain the limit answer. All right, box isn't working with me there, but that's okay. So what the proof shows is that if you take the limit as x goes to a of f of x over g of x, this is equal to the limit as x goes to a of f prime of x over g prime of x. And so because of this, what we have here is a really simple change that we can make, is that if you get an indeterminate form here, maybe when you take the derivative of both terms, the form will no longer be indeterminate. And that's the goal behind doing L'Hopital's rule, is to make this change of the original ratio with the ratio of the derivatives instead. All right, let's take a look at a couple of answers. So we'll start real simply here. We're going to take the limit as x goes to 0 of sine of x over x. Now what you should always do, and I want y'all to follow this as you're working through your problems, you're going to directly substitute. So if you directly substitute in, you get sine of 0 over 0, which is 0 over 0, and that is my indeterminate form. Now, if I'm going to apply L'Hopital's rule, I had to check that I was in one of these two cases. Remember, L'Hopital's rule only works if you're in the 0 over 0 or infinity over infinity case. Since we are in the 0 over 0 case, I know I have the correct indeterminate form. So that's always step one, is to check that you have the correct indeterminate form. And then if you realize it's if you realize it's the right indeterminacy, what you do now is to apply L'Hopital's rule. I'm going to say equals, and then I'm going to write an LH above the equal sign. This is indicating to the person reading the work, or the grader, which would be me, that from this step to this step, you're applying the rule that we just talked about, L'Hopital's rule. So L'Hopital's rule says I can take the limit, but replace sine with its derivative. So the derivative of sine is cosine. Replace x with its derivative. The derivative of x is 1. And then retake the limit. So if I plug 0 into the limit now, I get cosine of 0, which is 1, divided by 1. The answer is 1. So the limit as x goes to 0 of sine x over x turns out to be 1. And there's no amount of algebra from earlier in the course that's going to show us that. In fact, the only way for us to do this earlier in the course is to create a table, remember, where we have values approaching 0 from the left and right and seeing what it's heading towards. That's the only way we could have calculated this limit before, but now that we have access to derivatives, I can show that this limit is 1 analytically. I don't have to resort to a numerical calculation. All right, example 2. So I want to look at the limit as x goes to 0 from the right of x times natural log x. Now, here's the thing when looking at this problem. If I directly substitute in x equal to 0, natural log of 0 from the right, I get 0 times, remember the way that natural log function works. So the natural log function looks like this. So as we approach 0 from the right, it goes to negative infinity. So this is a 0 times negative infinity, or a 0 infinity type indeterminacy. So I know from what we talked about earlier that this is indeterminate. However, I can't use L'Hopital's rule here, at least not yet, because it's not 0 over 0 or infinity over infinity type. So I want to do some algebra first to turn it into the right type. I've got to create a ratio. So I've got to divide by something, but I can't change the original function. So here's, I think, the best way to go about this. You've got natural log of x in top, and then instead of multiplying by x, I'm going to divide by 1 over x, which is the same thing, right? Dividing by 1 over x is the same thing as multiplying by the reciprocal of that, which is x. So these are the exact same thing algebraically, but now I have a ratio of two functions. Let me plug the limit back in and see if I have the correct type of form now. So I've got natural log of 0 from the right and the top, and I have 1 over 0 from the right and the bottom as an indeterminate form. This is negative infinity for the natural log, and then 1 over 0, 1 over a very small number gets very big, and because it's approaching from the positive side, it gets very big positively. So this is an infinity over infinity type, and that is the correct type to use L'Hopital's rule on. So if I'm going to apply L'Hopital's rule here, I have got to use the correct form, which I now have. So L'Hopital's rule says take the derivative of the top, the derivative of the bottom, and recalculate the limit. The derivative of natural log is 1 over x, and the derivative of 1 over x is minus 1 over x squared. Now, if you get ahead of yourself and reapply the limit, you'll get infinity over negative infinity. So nothing will change here if you just simply plug 0 in. But if you notice that you can do a little bit of algebra, this is the same thing as negative x squared times 1 over x. Right? Dividing by this term is the same as multiplying by its reciprocal, which is negative x squared, times 1 over x. This is simply the limit as x goes to 0 from the right of the function negative x, which I can substitute the limit in for and is not indeterminate. If I plug in x equal to 0 at this point, so now I'm directly substituting the limit, I get negative 0, which is just 0. So the limit of this function as we approach 0 from the right is in fact 0. Once again, we wouldn't have had an algebraic way of doing that earlier in the course. All right, take a look at this example. We've got a fraction here on top. We're going to plug in 3. Fraction in the bottom, we're going to plug in 3. I want you to try it on your own, see what you can come up with. So pause the video and then we'll talk about it together. All right, if you haven't paused the video yet, please do so. First thing we have to verify, is it an indeterminate form? So I'm going to take the limit as written. I'm going to plug in the value 3, so I'm directly substituting in for x equal to 3. So this is 1 over 3 minus 1 over 3 over 3 squared minus 9, which is 0 on the top. 3 squared is 9, so 0 on the bottom. We have the correct indeterminate form. Now, apply L'Hopital's rule. I'm going to take the derivative of the top. The derivative of 1 over x is minus 1 over x squared. The derivative of negative 1/3 is a constant, so that is 0. In the bottom, the derivative of x squared is 2x. The derivative of negative 9 is 0. And simplifying this, you get negative 1 over x squared in the denominator along with 2x. So we get negative 1 over 2x cubed. If we then directly substitute in, and I should have wrote my LH here for L'Hopital's rule, going from here to here. So going from here to here, I used L'Hopital's rule. And if you directly substitute in x equal to 3, you get negative 1 over 2 times 3 cubed. 3 cubed is 27. 27 times 2 is 54. So if you selected answer choice D, you have the correct answer. All right, so here's a question that I like for L'Hopital's rule to make sure that you understand when you can and can't use L'Hopital's rule. So suppose a student was tasked with finding the limit as x goes to infinity of this ratio, and this was the work that they showed. The student reached the conclusion that the limit did not exist. Did the student make a mistake? So yes, a mistake was made, or no, a mistake was not made. I want you to make up your mind. Tell me if there's a mistake here. There may be more than one mistake, or there may be no mistakes. But make up your mind, and then we'll talk about it in just a second. All right, if you haven't paused the video and decided on an answer, please do so. Here's my take. Yes, there's definitely a mistake made. And in fact, there's probably two mistakes here. Let's start with the first mistake, which is the student tried to do the following. They used L'Hopital's rule right here, right? You can tell they differentiated x and got 1. The derivative of cosine is minus sine. The derivative of x is 1. Then they plugged infinity in, and they rightly got that this limit didn't exist because sine oscillates back and forth. It never settles in on a value, so 1 minus sine does not approach any particular limit value, so that limit would not exist. But that's also the same problem that plagues us in the original part. If you look at the original part, I've got a test for the right indeterminate form first, right? That's the first thing I have to do is determine, can I just directly substitute this in and get the correct form to apply L'Hopital's rule? And the answer is no, because you get infinity plus cosine of infinity over infinity. You might think that this is infinity over infinity type, but here's the thing. This limit doesn't exist because this thing is oscillating back and forth. Yes, these are going toward infinity, but this original limit does not exist in the first place. It's not that it's indeterminate, it just flat out doesn't exist. And because of that, I can't apply L'Hopital's rule. The other problem here is, remember, if we apply L'Hopital's rule and get that the limit does not exist, then L'Hopital's rule tells us nothing. So I can't conclude that the original, just because I did L'Hopital's rule and found this new limit didn't exist, that doesn't necessarily mean the original limit didn't exist. Here it meant it, but in general it doesn't mean anything about that original limit. So using L'Hopital's rule to verify anything in this situation is just, it's not appropriate. If you look at the function, another thing to think about here is you've got x plus cosine of x over x. This is the limit as x goes to infinity of x over x plus cosine of x over x, which is the limit as x goes to infinity of 1 plus cosine of x over x. If I'm going to be able to apply L'Hopital's rule in this problem, this limit here would need to be infinity over infinity or 0 over 0, but it does not exist over infinity. That's why this thing doesn't exist. This limit just flat out doesn't exist to begin with. So applying L'Hopital's rule to prove that, it's not something that we care about. It's not something that L'Hopital's rule is made to be used for, is probably a better way to say it. So yes, there's definitely a mistake here. All right, I want you to try this one. And I want to warn you before you try this one that sometimes when you do L'Hopital's rule, whatever indeterminate form you have, you'll do L'Hopital's rule and you have the same indeterminate form again, but there's something about the problem that makes you think if you keep doing L'Hopital's rule, which you can do as long as you have the right indeterminate form, that things will get better. And this is an example of such a problem where you can apply L'Hopital's rule several times and the result is something that'll come out better. So I want you to look at this, maybe work through L'Hopital's rule if you would like, and tell me how many times do you think we'll have to apply L'Hopital's rule to this example before we get an answer? All right, if you haven't tried this on your own and committed to an answer, please pause the video and do so and take a look at it together. We'll start with the limit as is and see if we have the correct indeterminate form. If I directly substitute in 0, I'll get cosine of 0 minus 1 plus 0 over 0. Remember, cosine of 0 is 1. So that's 1 minus 1, which is 0 over 0. We have the correct form to continue. So this is equal to, using L'Hopital's rule, so we've used it once now, the derivative of cosine is minus sine. The derivative of 1 is 0. The derivative of x squared over 2, the 2 comes down and cancels with the 2 that's already there, so this is just x over, this would be 4x cubed. So if I directly substitute in here, plugging in 0, I get minus 0 plus 0 over 0. Looks like a bunch of zeros to me. It's still the correct form where if I wanted to do L'Hopital's again, I could. It's still 0, 0, or infinity over infinity, so I can apply L'Hopital's rule again. So we're coming back to this point. The derivative of minus sine is minus cosine. The derivative of 0 is still 0. The derivative of x is 1. And the derivative of 4x cubed is 12x squared. Okay, keep going. See if we have a resolution to this. Whoops, it's not infinity, it is 0. So if you plug in the limit at 0 here, you get minus cosine of 0, which is minus 1. You plug in 0 to the bottom, you get 12 times 0, which is 0. Minus 1 plus 1 in the top, so once again, 0 over 0. At this point, you need to start asking yourself, is this ever going to end? Okay? Because there are some problems that can get caught in loops like this where it will never give you an answer and you're just kind of spinning your heels. Normally, that's when you have exponentials involved. But here we do sense a resolution is at hand because the denominator is getting smaller each time we do this. If we were to take L'Hopital's rule again, it'd be 24x. And if we do it one more time after that, it would just be 24, which means we won't have a 0 in the denominator anymore. So there's light at the end of this tunnel, so I'm going to keep going. Take the derivative of negative cosine, you get positive sine. Derivative of 1 is 0 over the derivative of 12x squared is 24x. Apply the limit here, you get 0 over 0. Remember, sine of 0 is 0. And this will be the last time we have to do it. Derivative of sine is cosine. Derivative of 24x is 24. If you plug in cosine of 0, so directly substituting, cosine of 0 over 24, cosine of 0 is 1, divided by 24. It turns out that this limit, which made us do L'Hopital's rule 1, 2, 3, 4 times, so congratulations if you picked E. It's a long problem, but it's one of the interesting things that can happen when you try to apply L'Hopital's rule, is that you might be put in a position to do it over and over and over again. All right, so how do we handle this limit? And at no point in the course have we been able to do these guys. X to the x power. We started to talk about taking derivatives of these recently, and remember that required logs. And so it's probable that this is going to require a log as well. But it's not in the correct form for L'Hopital's rule. If you look, in its current form, it's of the form x to the x, which is indeterminate, right? This is indeterminate. We talked about that at the beginning of this lesson. But it's not, I shouldn't have put a check mark there, but it's not the correct kind of indeterminate form to apply L'Hopital's rule. So we're going to use a trick that we used when we were first introducing the derivative of x to the x. And that is, recall that I can write x as e to the natural log of x. So what this means is that x to the x is e to the natural log of x to the x, which our properties of exponents tell us this is ex natural log of x. Those are the same thing. So you can write x to the x as though it were this. Simple enough. So I'm going to take my limit and I'm going to rewrite it using what I just showed. So I'm going to take x to the x and rewrite it as e to the x ln x. Now remember, properties of limits, if you have a limit of an exponential, you can take the limit of the exponent. So this is the same thing as just the limit popping up here into the exponent. And we're taking the limit of x ln x as x approaches 0 from the right. Now, thankfully for us, we've already done that today. If you recall, I believe it was example 2, right here, we took the limit as x went to 0 from the right of x ln x and found that that limit was 0. We had to divide by 1 over x to get it in the right form, and then we found that the limit was 0. So we know that this limit does require L'Hopital's rule. So it requires L'Hopital's rule to do this limit in the first place. See example 2. And that limit turns out to be 0. So we get e to the 0, which is 1 here. So it turns out that the limit as we approach 0 of 0 to the 0 is 1, which means that the exponent is sort of winning that battle because the exponent wants to make this thing 1. All right, so one final example to take a look at here. This is an applied example where L'Hopital's rule can be useful. Suppose we have a metal cable. So the metal cable here, let me make that a little bit bigger. So we've got a metal cable, and the cable has radius r. Okay. It's covered by insulation so that the distance from the center of the cable to the exterior of the insulation is big R. So here's the insulation. And the distance from the center to the outside, this distance, well, the whole, I don't want to confuse you here, this whole distance is big R. And so all this is out here, this is just insulation. All right, so here's what the question asks. It asks us to find the following limits and interpret our answers. So what is the limit as r approaches r from the right of v, and v is the velocity at which an electrical signal travels through the cable. So we've got some sort of electrical signal being sent. The velocity at which that signal propagates is a function of the amount of insulation and the size of the cable through which it's propagating. So I'm taking the limit of this function here. And here's the way that L'Hopital's rule works. You always take the derivative with respect to the part of the problem that is moving. So the value of the insulation is moving, and so as r approaches little r in size, that means the insulation is approaching 0. So another way of talking about this limit is we're looking at what happens as the insulation size approaches 0. So what happens to the speed? Okay, if you take the limit here as r approaches, we're just going to directly substitute in. So you'll get minus c. I'm replacing capital R with little r. So capital R gets replaced with little r. And in here, capital R gets replaced with little r. And so what you have is negative c r over r squared. Well, r over r is just 1. So this is approaching 1, natural log of 1. So natural log of 1 is 0, if you recall. So this says that the velocity slows down as you decrease the insulation. And that is because if there's no insulation, then the electrical signal loses, it just loses signal to the outside environment. It sort of diffuses isn't the right word, but it loses to its outside environment. So eventually the signal just gets lost completely. This is the importance of insulation for signals. Okay, so that's A. What about B? So B asks you to look at the limit as r approaches 0 from the right of the same function. Okay, so r approaching 0 means this radius is getting smaller. It's asking me to describe what happens as the cable gets smaller, right? So we're looking here at the speed of the signal as the cable shrinks in radius. And here this is the speed of the signal as the insulation shrink to 0. Okay, so I'm going to directly substitute in. This would be negative c. I'm making r equal to 0, so we'd have 0 for this term, times the natural log of, if you plug in 0 here, natural log of 0. So we've got 0 from the first part here. This is 0. And this part is negative infinity. So I have a 0 infinity type, which is indeterminate. But it's the wrong kind of indeterminacy for L'Hopital's rule, so let's see if we can make it the right one. So to apply L'Hopital's rule, we're going to write this limit as negative c over, and I'm gonna keep the r squared part here. I'm going to keep that out with c because they're both constants. And I'm going to take this r squared part, I'm going to put it on bottom, just like we did on example 2. So this is going to be the natural log of r over r divided by 1 over r squared. So this is the same as this, right? Algebraically, these are identical. And remember our rules of exponents here. I can take and factor out any constants, which makes this much nicer to look at. and we're just dealing with the natural log of r over r divided by 1 over r squared. And if I plug in 0 once again, I get negative infinity in top. If I plug 0 into the bottom, I get positive infinity. This is the correct indeterminate form for us to apply L'Hopital's. So if I apply L'Hopital's rule now, I'm looking at this form here. I've got minus c over r squared. I'm taking the limit as r approaches 0 from the right. And what I'd like to do is differentiate both pieces. So the derivative of natural log, if you recall, is 1 over whatever's inside there. So 1 over that is simply the reciprocal of that. Times, because of chain rule, times the derivative of this with respect to the thing that's moving, which is r. So the derivative of this with respect to little r is 1 over r. So that's the derivative of the top. And then the derivative of the bottom, this is r to the negative 2. So this will be negative 2 r to the negative 3. And so if I clean this up a little bit, this is in the top. You've got the big r's cancel out. You've got 1 over r. And you should be careful here because this r here is in the denominator, but the r that's already in the denominator is a negative r, so it's actually in the numerator. So this r is in the denominator, this r is in the numerator. So you're going to have r cubed on top, and then you're going to have negative 2r in the bottom. That simplifies into, I'll bring the negative 2 out. R cubed over r is just r squared. So if you take that limit as r goes to 0, that's just going to be 0. So this limit is 0. So that makes a ton of sense. As r approaches 0 from the right, you've got less surface area to send the signal through, so the speed is going to slow down. So bigger cable allows for more speed, more insulation allows for more speed, but as you shrink those two things, we've shown in both cases here that the speed does go to 0. All right, that concludes our talk on L'Hopital's rule. There are several extra videos available for you for L'Hopital's rule, so take a look at those in addition to what we talked about today, and you should be good to go for Friday's quiz. All right, feel free to email me if you have any questions, and I'll talk to you soon. Bye.